Okay. Start okay. All right. So hello guys, good evening. Hello everyone. So welcome to today's one shot. So today we will have a one shot on electric charges and fields. Okay. Basically the first chapter in class 12 physics. So I guess the audio is fine. Audio is okay, no sir? Okay. Okay. So in today's one shot we will try to cover everything, which is basically we start from the charge and its properties. Then we will talk about Coulomb's law. Okay. Coulomb's law, we will talk about when the medium, when the charges are inserted in a dielectric medium also. Then we will move on to field. Okay. Once we are done talking about force, we will talk about electric field. And then finally, this is the lengthier part, which is electric flux and Gauss law. Okay. So that's how the order of topics will be. So this is how it's going to be, and at the end we will cover electric dipole. Okay, so lecture duration will be approximately 3 hours. Okay, we'll try to wind up within 3 hours. Okay, so during the lecture, guys, make sure you guys also make your notes. Okay, so make your notes, guys. Even though you will get this lecture PPT after the lecture, but you should make your own notes. That will be the best. Okay. So I guess with that we can start. We can begin today's lecture. Okay. Just give me a second. Okay. All right. So we'll start from the first topic, which is electric charges. Okay. So electric charge is basically just like just like mass, it's a fundamental property of matter. So basically all matter, as you all know, it's made up of, if we consider any object, okay, or any matter, it is made up of atoms, right? At the end of the day, it is made up of atoms, a bunch of atoms, and inside the atoms, we know within the nucleus there is protons, right? So protons carry positive charge, and surrounding the protons we have electrons as well. So all matter are made up of atoms, and within atoms we have electrons and protons, right? Electrons and protons. So these are, you can say, fundamental particles of nature, and electron has a negative charge and proton has a positive charge. So we'll discuss about their charge after some time. But the main idea of charge is that it's a property of matter through which it can experience electromagnetic forces. Okay. So in the first chapter, we will only focus on electrostatic forces. But basically, if we have two objects which possess charge, okay, and they are, let's say, positively charged, charge can either be positive or negative. Okay, so an object can either be positively charged or it can be negatively charged. So if we have two objects which are positively charged, then they will interact by the means of electrostatic forces. Okay, and you guys must have studied this. If we have two like charges, then they will repel each other. Okay, and this repulsive force is electrostatic in nature. Okay, this is the electrostatic force, repulsion force. We will study the magnitude of this force in Coulomb's law. Then it's the same story if we have two negative charges as well. In this situation also, they will repel each other by means of the same force, electrostatic force. But when we have unlike charges, which means positive and negative, then it is observed that these two charged particles, they will attract each other. Okay, this force is actually attractive in nature. But this electrostatic force is only observed if the body possesses some charge. Okay, if let's say one body had no charge, over here, if we consider any two bodies that are neutral, okay, no charge implies it's a neutral body. So I'm going to write it as neutral here. Okay, if we take two neutral bodies, then here there is no interaction, there is no electrostatic interaction. Okay, there is no electrostatic interaction or electrostatic force. So for electrostatic force to be present in the system, there must be charges present in the system. Okay, without charge, they cannot interact electrostatically. Similarly, there is another force called magnetic force, which we will cover in magnetism chapter, but that is also only felt by those charges, those particles which have a charge. Okay, so we will learn later that whenever we have a magnetic field, okay, and we have a charged particle, okay, a particle with some charge, and if it is thrown into the magnetic field, okay, with some velocity, then this experiences a magnetic force. This experiences, the charge experiences a magnetic force. Okay, this we will study in magnetism, or most of you have studied it probably, right, in school. But this, for the particle to experience either a magnetic force or an electric force, the object must have charge. Okay, so the electric charge you can in one line define as that fundamental property of matter by which it can experience electromagnetic forces. Okay, electromagnetic, that term consists of electric and magnetic. Okay, so both electric and magnetic forces can be felt or experienced by that matter which has charge. Okay, and there are essentially two types of charge. If we say an object is charged, it can either be positively charged or it can be negatively charged. Okay, the other is basically uncharged or neutral, which we will discuss. And this is the topic, this is the idea we discussed in the previous page. The like charges, they repel each other, and the unlike charges, they attract each other. Okay, and like and unlike, I hope it is clear. Like means they are of the same type, which is positive positive or negative negative, and unlike charges mean they are positive and negative. Okay, and electric charge, it is measured in this SI unit known as coulombs. Okay, its spelling is COULOMB. So this Coulomb is actually a very large unit for measuring charges. Okay, it's actually, so 1 Coulomb, it's a very large amount of charge. Okay, it's an extremely large amount of charge. So usually in our syllabus, most of the charge that we'll be coming across will be in amounts of microcoulombs. Okay, so if 1 microcoulomb is given, micro, guys, this you should keep in mind, micro means 10 to the power minus 6. Okay, 10 raised to the power minus 6 coulomb. Okay, that is what we mean by 1 microcoulomb. So okay, most of the time we will come across microcoulomb amount of charges, and sometimes we will come across millicoulomb amount of charges. This means 10 raised to minus 3 coulomb, and nano coulomb stands for 10 raised to minus 9 coulomb. Okay, so we will be only dealing with such tiny amounts of charge. Okay, and because 1 coulomb is an extremely large amount of charge. Okay, so that is it about charge. And the other question that could be asked is the dimension of charge. Okay, the dimension of charge, right? This can be asked. So for this, the thing is, you should, whenever a dimension is asked, you should always relate it to some other formula which you know. So in class 10th, you would have learned the formula for current, right? Current was basically the ratio of charge over time. So in this formula, we actually have charge present here, right? So we can get the dimension of charge using this result. So dimension of charge, so for charge we usually use the symbol Q, capital Q or small q. So dimension of charge will be dimension of current into dimension of time, right? Now current is a fundamental quantity, okay? So we will write it as ampere raised to power 1, and time is also a fundamental quantity, so we will write it as t raised to 1, okay? So this will be the dimension of charge. It is ampere power 1, time power 1, okay? So yeah, that is basically it. That's the dimension of electric charge. Now we can discuss some properties of electric charges, okay? The first thing is, how are charges added? How are charges added? Or you can say additivity of charge. Okay, so this is actually very simple. So let's say there is one system. So system, you can just consider it as a box, okay? And this box has a Q1 amount of charge, and another box has Q2 amount of charge, and another box has Q3 amount of charge. And you want to mix the amount of charge in these three boxes, which means you want to add up these charges. Then the final box will have a charge of, simply just add them up, okay? Q1 plus Q2 plus Q3, okay? So charges are simply added like numbers, okay? So for example, if Q, instead of Q1, I take an example of 10 microcoulomb. Let's say Q1 is 10 microcoulomb, Q2 is minus 12 microcoulomb, and Q3 is 20 microcoulomb. Then what will be the total charge in the system? The total charge in the system will be 10 plus 20 is 30, 30 minus 12 will be, wait a second. Yeah, so this is minus 12, so minus 2, 18, right? So 18 microcoulomb will be the final answer. And how did I do it? 10 minus 12 plus 20. Okay, you basically add them up like numbers. Positive charges you will put with a plus sign, and negative charges you will put it with a negative sign, okay? So that's how charges are added. You basically add them like numbers, okay? So that's basically, in other words, that means charges are also scalars, right? Because a scalar quantity is those quantities which can be added like numbers. Mass is another example for that, right? So that's basically it. So whenever you have a system which has Q1, Q2, Q3 and so on until Qn charges, if you want the total charge, you simply add them up, okay? So that is it. There is nothing complicated here. Then the next thing is conservation of charge. Now conservation, this term is pretty commonly used in physics. So what do we mean by conservation? Conservation simply means it's a constant, okay? So if we say that charge is conserved, we are just saying that, in other words, charge remains constant, okay? It cannot be created or destroyed. So what we mean by that is, if I give you an example where in a box we initially had some capital Q1 amount of charge, okay? And in another box, or let me give you another example. Let's take numbers. So in one box, initially there was 20 microcoulomb charge, and in another box, there was 30 microcoulomb charge, okay? Now, some charge from this box was taken to the other box, okay? And it is given that finally box number 1 only had 10 microcoulomb charge. Then the question is, what is the charge in the other box? This is the question. Okay, so this is actually very easy. the total charge in the system is charge in box 1 and box 2, right? So that will be 20 microcoulomb plus 30 microcoulomb. This is the total charge. If we take these two boxes together, this must be the same in the final case also. So in the final case, the charge 1, the box number 1 has 10 microcoulomb, and box number 2, let's take it as let's say it has Q charge. Okay. This must be true. The total charge before any process is equal to total charge after any process. Okay. So this is 50, 50 minus 10 is 40. So charge in box 2 is 40 microcoulomb. So basically the thing is, if charge cannot be destroyed or created, okay, the total charge here was 50, so finally also it should be 50, which means the charge here should be 40. Now, that is basically the idea of charge conservation. Okay. So now the thing is, there is also another interesting thing. That is about neutral bodies. What do we mean by a neutral body? Okay. So neutral body, this is a confusion that some students have. When we talk about neutral body, this does not mean no charge. Okay, this does not mean no charge is present in the body. Okay. So if we have a body, when we say it's a neutral body, that does not mean it does not have any charge inside it. But what it means is it has equal number of positive and negative charges. So neutral body implies that it has equal number of, so negative charges are basically electrons, right? So electrons, we write it as E minus. So equal number of electrons, and protons we write it with a P sign, okay, and protons. So if any body has equal number of electrons and protons, then we call it as a neutral body. Okay. So that does not mean it doesn't have electrons. Okay. But if it has, let's say, 3 electrons, it will also have 3 protons. Okay. So in this case, the total charge will be 0 because it has equal amounts of electrons and protons. So that is what we mean when we say we have a neutral body. Okay. So the next important idea is quantization of charge. Okay. And questions have been asked from this topic for CBSE board exams. Okay. So the idea is pretty simple. So quantization of charge, we can understand it if we understand how is a body charged. Okay. So let's take our original neutral body itself. Let's take our original neutral body itself. And what does neutral mean? Neutral means equal amounts of protons and electrons. Okay. Now there should be some, this fact you guys should be knowing. Okay. For electron, the charge of the electron is minus E. Okay. And what is this E? E's value is, this is also important, guys, 1.6 into 10 raised to minus 19 coulombs. Okay. So the charge of an electron is firstly a negatively charged particle. So it will be minus E. And the E's value is also important, 1.6 into 10 raised to minus 19 coulombs. And what about proton? Proton is the opposite of this. It's a positively charged particle. Okay, and its charge is plus E, the same E as the electron. So the electron and proton have equal charges in magnitude, but their sign is different. Electron is negatively charged, proton is positively charged. Okay. Now, in our neutral body, let's say we want to charge this neutral body. Okay. So how can we do it? One way is to remove electrons. Okay. So let's say there was this one electron over here and we pulled out this electron using some mechanism. We are going to remove an electron, remove one electron. Okay, so we have our original neutral body. Okay. Think about what happens to the body now. So finally, let's say the body has some q charge and we removed an electron. So that electron we will write it here. Okay. So what we did is initially we had a neutral body. So net charge will be 0. And then we removed an electron. We pulled out an electron. So now use charge conservation. Initially charge is 0. Net charge is 0. Finally, the charge on this body, I am saying it is some q. What is the charge of an electron? Charge of an electron is minus e. So write it over here. Now solve this. This means q is equal to plus e. Q is equal to plus e. If you take this e to the other side, q is equal to plus e. Which means this neutral body which we had, if you remove an electron, its charge will increase by plus e. Okay. This is actually pretty easy. Neutral body's charge is 0, right? Electron's charge is minus e, right? So which means this body's charge must be plus e. So that plus e minus e will be 0. Before and after charge has to be the same, right? Now let's say we pull out one more electron from this neutral body which is charged to plus e. We pull out one more electron. Remove another electron. So far we removed 2 electrons, right? So now the charge on the body will be plus 2e using the same logic. Okay. So my question is, if we pull out n electrons from the same neutral body, okay, from the neutral body, if I remove some integer number of electrons, let's say n electrons, okay, n is some integer, then what will be the new charge? Then the thing is, this body will now be positively charged, right? It will be positively charged. And the new charge will be, so minus Ne was removed. So the charge on the neutral body will be plus Ne, right? Because n electrons were removed. So this is how we charge any body. We remove electrons one by one, okay? Or we can say we remove an integer number of electrons from any body, and that's how we charge up an object. So when we say an object is charged, it must be of the form, the charge on the body must be of the form n into e, right? Because we cannot remove a fractional amount of electrons. We cannot remove half electrons. We can only remove integer number of electrons. So it can be either 1 electron, 2 electron, 3 electron, or let's say 1000 electron, but we cannot remove a fractional amount. This is what we mean by quantization of charge. So the charge on any body, it can only be in the form of some integer number of this E. E is the charge on a proton or an electron. Okay. This N can be positive or negative. Okay. It can be positive or negative, but it must be an integer. You cannot have n as a fraction. So let's say n is equal to 3 by 2 you are choosing. This is not possible. This is not possible. This means you are removing 1.5 electrons from a body, which is absurd, right? You cannot remove a fractional amount of electrons from a body. That must be in the form of some integer. Okay. So that is the idea of quantization of charge. A body can be charged only in Ne amounts. Okay. It cannot be charged by a fractional amount of E. So that is basically quantization of charge. And this is something that you guys should remember. Electrons charge is minus E and protons charge is plus E. And the amount, the value of E is also very important. Okay. Which is 1.6 into 10 raised to minus 19. Okay. So we can do a question on this quantization of charge. Yeah, so this question, so this has been asked in CBSE itself. So it's given that a body has acquired a charge of 8 into 10 raised to minus 12 coulombs. Okay, a body has acquired this much amount of charge. And how did this body acquire the charge? By removing some electrons from it, right? If a body is positively charged, like this is a positive charge, right? Which means electrons were removed, which means electrons were removed. Electrons were removed, right? That is what we mean. That is how this object became positively charged. So, if electrons were removed, let me say that n electrons were removed, right? I am saying the number of electrons that were removed is n. So, what will be the charge on this body? It will be plus Ne, right? It will be plus n into E. But the charge is given to us. It is 8 into 10 raised to minus 12. Now solve it. So E will be 1.6 into 10 raised to minus 19. And this will be equal to 8 into 10 raised to minus 12, right? So 1.6, 16 cancels out with 80, 5 times, right? So the number of electrons, you can get it now, 5 into 10 raised to 7. This much electrons were removed from the object, and that's how it gained this much charge. Okay. Now the main question is the mass of the body is increased or decreased by what amount? So what does that mean? Why are they asking the mass of the body changed? That is because how was the body charged? By removing electrons, right? Now electrons also have some mass. So which means some mass of the part of the body was also removed. So what is the mass of an electron? Try to remember that. Mass of the electron was 9.1 into 10 raised to minus 31 kg. This value is also important. Okay. I guess you guys must have studied this in chemistry. So mass of one electron is that much approximately. So this many electrons were removed. So what was the mass removed? So the mass removed, you just have to multiply these two numbers, right? So the mass removed will be, so 9 5s are, take it as approximately 45.5 I guess. That is what you will get if you multiply 9.1 and 5. And 10 raised to minus 24, right? 10 raised to minus 24 kgs. 31 and 7, if you subtract from that, you will get 24, yes. So which option matches? Option B. So if we divide, this will be 4.55 into 10 raised to minus 23. So this is the amount of mass. It's a very small mass, right? Negligible amount of mass, because electrons are very light, right? Electrons order is 10 raised to minus 31. So it's a very tiny mass. So even though 50, what is this? 50 million, right? Even though 50 million electrons were removed, the mass removed is still a very tiny amount. Okay. So the answer is it decreases because electrons were removed by this much amount. Okay, by this much amount. So that is it. Now, if in the same question, this was a negative 8 into 10 raised to minus 12, right? If the charge on the body was given to be negative 8 into 10 raised to minus 12, then the logic is exactly opposite. If you want to positively charge an object, you remove electron, right? If you want to negatively charge an object, you add electron. Okay. If you want to negatively charge a neutral body, then you add negative charges, right? Which means you add electrons. Add electrons to the body. Okay, which means in this case, of course, the number of electrons will still be the same added. It will be the same as last case, 5 into 10 raised to 7. But in this case, the electrons were added to the body as opposed to removed. Okay. So in this case, if I ask you what happens to the mass, the change in mass or delta M, this would increase now. Okay, this would increase because now electrons are added to the body, right? So the mass of the body will increase by this much amount in that case. Okay, so if this, instead of this being positive, if it was negative, then the mass of the body will increase. Okay, because electrons are now supplied to the body. Okay, if electrons are added to the body, it becomes negatively charged. If electrons are removed, it becomes positively charged. Okay, so that is it here. Now we will talk about a certain mechanism of charging a body, which is by rubbing two objects. Okay, and then we'll discuss an experiment which is given in NCERT. So if we take any two objects which are made of different materials, okay, material A and material B, okay, and assume for a second they are not conductors, they are some insulators. Okay, insulators means they don't allow flow of charge through them. And we pick up these two objects and rub these objects together. Okay, we pick up these two objects. Okay, we pick up B and basically rub it on A. Okay, we rub it on A. So what happens is, during rubbing, or basically while rubbing the two surfaces, okay, these two materials, these are made of different materials. Okay, while rubbing the two surfaces, what happens here is there is an electron transfer from one body to the other. Okay, forget about which body gains the electrons, but the electrons that are lying on the surface of A, let's say it jumped into B. Let's say it jumped into the surface of B. Now what do you think will happen? This was a neutral body, right? Both of them initially at the start was neutral. Both of them were neutral at the start. But now what happens? A has lost electrons. Okay, electrons from A jumped into B, so A lost its electrons, right? So A will become positively charged. A will become positively charged. Let's say its charge is now some plus Q. Okay, its charge is some plus Q. What happens to B? B gained some electrons, so B will become negatively charged, right? B will become negatively charged. So it will gain a charge of minus Q. So this is what happens when we rub two different materials, rub the surfaces of two different materials together. Okay, what happens is electrons from one body jumps into the surface of the other body, and as a result one body becomes positively charged and another body becomes negatively charged. Okay, this method is known as charging by friction. Charging by friction. Okay, so in NCERT, the first in the first starting of the chapter, they have given this experiment of the silk rod, of the silk cloth and glass rod. Okay, so this experiment is basically simple. First we take two glass rods and we rub it with silk. Okay, so, you can also use wool cloth, and what happens is when you rub the glass rod, if let's say this is the glass rod, and when you rub it with silk, when you rub it with the silk cloth, what happens is the glass ends up losing its electrons to silk, and as a result the glass rod becomes positively charged. Okay, now who gains the electrons and who loses the electrons, that has to be experimentally determined. Okay, you cannot just there's no mechanism with which we can say that the glass rod lost its electron. We have to experimentally determine it. Okay, so the glass rod ends up losing its electron to silk, which means the glass rod will become positively charged and the silk cloth will become negatively charged. Okay, that is what ends up happening. Now in the experiment, the thing is we took two different glass rods, okay, and we rubbed it with silk cloth. Okay, we rubbed it with silk cloth. So what happens when we rub it with a silk cloth? The glass rod becomes positively charged, right? And one of the glass rods, we hung it to a thread and we brought another glass rod close to it. And what was observed was this glass rod actually repelled it, right? That this glass rod experienced a force, a repulsive force. So from the side view, it will look like this. If this is the thread hanging the rod, and let's say this is the glass rod that is positively charged. What was observed is when we brought the second glass rod, this rod felt a deflection, right? This rod felt a sideways push, a repulsive force. Okay, and that is straightforward because like charges repel each other, right? So that's why these two rods actually repel each other. So this you can actually remember that if you rub a glass rod with a silk cloth, the glass rod is what becomes positively charged. Then the second experiment is a plastic rod with a cat fur. Okay, so this is the first experiment that is mentioned, and the second experiment we have been given a plastic rod that is rubbed with fur. Okay, like cat fur. It's mentioned as cat fur in NCERT. In this case, actually the opposite is what is happening. The fur loses its electrons to the plastic rod, and hence the plastic rod becomes negatively charged, which means the fur will become positively charged. The guy who loses electrons becomes positively charged, and the guy who gains electrons becomes negatively charged. Okay, and now once again, if you bring two plastic rods close together, negative and negative will repel each other, right? So this rod will also be repelled away. Now if you bring the glass rod from the first experiment close to the plastic rod from the second experiment, now these two will attract each other because the glass rod is positively charged, right? And the plastic rod is negatively charged, and unlike charges will attract each other, right? So now the thing is the force between them will be attractive. So this is actually historically one of the first experiments which helped us discover electric phenomena, right? So this is actually one of those experiments which helped us discover electric charge. Okay, so then what happened was basically scientists concluded that there are essentially two types of electric charges. One type of a charge was called positive charged and the other one was negative. Okay, this was randomly allocated. Okay, there's nothing special about positive or negative. And then this was observed in the experiment. If you have positive and positive charge, they repel. Negative and negative also repel, and positive and negative also that will attract, unlike will attract each other. Okay, so that is it. This is actually what the first experiment given in NCERT is, and this can be asked. Okay, they can ask question like in the glass rod and silk thread, what charge does the glass rod obtain? Those type of questions can be asked. So I have given this table also which summarizes who gains what charge. Okay, then there is this question. Okay, not this one. So like if you guys can attempt a poll, then you guys can try this out. Okay, I'll start a poll for 60 seconds. Okay, if you have the PyLens app with you, you can attempt this poll. Okay. The question is, the glass rod is rubbed with silk and it acquires positive charge because. What is the reason exactly? Gayatri is asking, is this enough for mains in advance? But no, this Gayatri, this is essentially for the board exams. Okay. Um, so this whole series is mainly for the board exams. Okay, it's to quickly revise everything for the CBSE level. Okay. This is not a mains level revision course or an advanced level. Okay. Okay, so the answer is the glass rod, it acquires a positive charge, right? As discussed, the glass rod, it acquires positive charge. And the mechanism was, the guy who attains positive charge has lost electrons, right? So the glass rod lost its electrons. That's why it became positively charged. So electrons are removed from it is the right answer. Option D. Let's see. Yeah, so basically I don't think you guys have access to it, but I hope it is clear. Okay. I hope it is clear. Protons are never messed with in any of these experiments. Okay. Whenever charge transfer happens in any question, when we are studying electrostatics or any chapter, electric current, it's always the electrons that are moving. Okay. Protons are tightly held inside the nucleus. You cannot just simply pull them out. Okay. So it's always electrons that are either removed or added. Okay. Okay, then there is this one question. This is actually an NCERT problem. Okay. This is given in one of the exercises in NCERT. So we have 10 raised to 9 electrons that move out of a body to another body every second. Okay, so they're saying from the body, 10 raised to 9 electrons are removed per second, right? So in t seconds, it is easy, right? Just use the unitary method. If 10 raised to 9 electrons are removed in 1 second, then in 2 seconds, it will be 2 into 10 raised to 9. And in t seconds, the number of electrons removed will be t into 10 raised to 9. Okay. So after t seconds has passed, the number of electrons removed will be t into 10 raised to 9. In this case, what will be the charge of the body? If I say the charge is Q, I can say Q is actually the number of electrons that were removed, which is this much, into charge of 1 electron, which is E. We want this charge to be equal to 1 Coulomb, right? We need to find out when does this become equal to 1 Coulomb. So now we can solve for that time. So time t will be 1 Coulomb divided by 10 raised to 9. And what is the value of E? E is 1.6 into 10 raised to minus 19. So this will end up being 1 divided by 1.6 into 10 raised to 10, right? 10 raised to 10 seconds. This is actually a very large quantity of time. So this will be 0.625, I guess. Let me see. So it will be 5 by 8. So 10 by 16, so 5 by 8. Is that correct? Let's me. Yeah, 0.625 is the answer. It is this thing into 10 raised to 10 seconds, or you can write it as 6.25 into 10 raised to 9 seconds. Okay. So it will take us this much time for the charge to become 1 coulomb. Okay. The more electrons are removed, the more positive the charge will become. So after t time, we want it to be equal to 1 coulomb. Okay. So that is the question. Now that is it about the charge transfer and quantization of charge. Now we will talk a little bit about conductors and insulators. So conductors and insulators, mainly we will deal about these in current electricity. Okay, but right now we can just simply discuss them at a fundamental level. So conductors and insulators are basically types of materials. Okay, conductors are those types of materials that allow electricity to flow through them. Okay, electrons to flow through them. So basically, if I choose a conductor, a material that is made up of so conductor, you can take an example of a copper wire. Okay, a metal. Metals are good conductors of electricity. And near this conductor, I brought a very large positive charge. Okay, very big positive charge. Then the thing is, because conductors allow flow of electrons inside it, from everywhere inside the conductor, the electrons are present everywhere, right? Everywhere inside the conductor. So what happens is, because of this positive charge, the electrons are negative, right? So they will feel an attractive force to the right. So what happens is, all these electrons will run towards the right end and they will gather at this location. Okay, as a result of the attraction due to the positive charge. Free electrons gather near the positive charge. Okay, near the positive outside charge. Okay, so that is the whole point of a conductor. A conductor allows electrons to freely move inside the material, but an insulator does not. Okay, if you bring a positive charge like that in front of an insulating material, the electrons just cannot respond to that plus and run away to one side. Okay, so insulators, you can just say that the electrons are rigidly attached inside the atoms and they cannot freely flow, whereas conductors allow the free flow of electrons. Okay, and then you can remember these material examples as well. Metals are very good conductors of electricity, as you all know, and insulators example would be glass, porcelain, plastic, right, wood. These are good insulators. So we will cover insulators and conductors in detail in current electricity. Okay, but for now this is enough. Okay, the main point is, inside conductors, the electrons can freely move anywhere they want. Okay, and these types of electrons are called free electrons. Okay, the reason why they are called free electrons is because they are free to move inside the material of the conductor. Okay, yes, so now let's get started with Coulomb's law. So Coulomb's law essentially tells us about the magnitude of that electrostatic force which we covered over there, right? So we understood that like charges repel and unlike charges attract. Coulomb's law is an experimental law which tells us about the magnitude of this force. Okay, so mathematically, what is that magnitude? That is what Coulomb's law tells us. So if we have 2 point charges, and point charges mean basically points. Okay, like mathematical, in maths you learn about point, right? So that point itself, but it has some charge associated with it. So Q1 and Q2. So I am choosing the two charges to be having a charge of Q1 and Q2, and I'm saying they are both positive charges. Okay, if they are both positive charges, then by common sense you can just directly say that these will repel each other, right? So their direction of force, so this force, so this is the blue line, and this Q2 will be repelled in this direction, and this Q1 will be repelled in this direction. And let's say the force of this repulsion is F. Okay, let's say the force of repulsion is F. We have to find this force F is what Coulomb's law tells us, the magnitude of this force F. And this is actually equal to K, which is just a constant, Q1 Q2 by R square. Okay, so the Q1 Q2 by R square is the important part. The greater these individual charges, the greater Q1 and Q2, the larger the force, and the further away these charges are from each other. R is basically the distance between these two charges. The distance between these two charges is what R is. Okay, this distance is actually R. So the further away these two charges are, or the greater the value of R, the smaller the value of the force. Okay. So that is how this force depends upon. It mainly depends upon Q1, Q2 and this distance R. Okay, first we will talk about the medium as vacuum. Okay, there is no medium surrounding these two charges. Okay, it's simply vacuum. Now this constant K is actually in SI units. So this is just a constant at the end of the day. And in SI units, its value is approximately 9 into 10 raised to 9. Okay, it's easy to remember because there are two 9s here. And what will be the units? Just use the rest of the stuff. So units of K will be Newton meter square divided by Coulomb square. So the units will be Newton meter square divided by Coulomb square. This will be the unit of this constant K. Okay, this is an important value to keep in mind. So that is your Coulomb's law. If you know the magnitudes of the charges and if you know the distance of the charges from each other, then you can find the force acting on those two charges, right? The repulsion, the repulsive or attractive force. Then the thing is, there's also a slight modification of this formula. This constant K, it can be also written as 1 by 4 pi epsilon naught. Okay. Why are we doing this? This is for convenience. Okay, this actually later on we will study something, another law called as Gauss law. Okay, the Gauss law expression will look better if we write K in this manner. Okay, so this is just a matter of convenience. There is no special reason to write K like this. Okay, it's just a constant at the end of the day, and pi and epsilon naught are also constants itself. Okay, so just to keep in mind, K can also be written in terms of other constants like this 4 pi epsilon naught, and this constant epsilon naught has another name to it. Okay, there are a few things to remember here. The epsilon naught constant also has another name to it known as permittivity. Of free space. Okay, free space just means vacuum. Okay, and this is just another constant. There's nothing special about this. You know, if we are talking about only vacuum, there is nothing special about this, and its value is 8.85 into 10 raised to minus 12. Okay, its units will be reciprocal of K. So which is reciprocal of this, it will be Coulomb square per Newton meter square. So this is your Coulomb's law. We will do some questions as well. Now the only thing additional, okay, before that, we will do a few questions, okay, on Coulomb's law. So in the first question, we have 2 point charges, 2 microcoulomb and 3 microcoulomb, and they're placed 20 centimeter apart in air, okay. The electrostatic force between them. So basically, this is just a direct application. So we have two charges that are 20 centimeter apart, and one charge is plus 2 microcoulomb and the second charge is plus 3 microcoulomb. Because they are positive, the force will be repulsive. So this guy will be repelled away by 2 and this guy will be repelled away by the 3 microcoulomb. Both of them will be repelled by the same force F, same electrostatic force F, and this force will be given by K, which is 9 into 10 raised to 9. Q1, Q2. So Q is in microcoulomb, so you have to convert it into SI units. So 2 into 10 raised to minus 6. And 3 microcoulomb will be 3 into 10 raised to minus 6 K Q1, Q2 divided by distance squared. So this also you should convert it into SI units. So if you divide it by 100, it will be 0.2. 0.2 is actually 1 by 5. So 1 by 5 square. Okay, so what does this come out to be? 9 2s are 18. So this is 25, right? 25 into 2 will be 50. 50 into 27 multiplied with 10 raised to minus 3. It's a force, so the unit will be Newton. So this, I guess, comes out to be option B. Okay, 50 divided by 100 is half. Yes, it comes out to be option B, which is 1.35. Okay, 1.35 Newton. So the calculation you guys can do, I am just explaining the concept. Okay, so yes. I'm not paying attention to the chat, okay. I'll just focus on teaching for now. But if you guys have any doubts, you can ask, okay. You can put it in the chat. So I'll teach for some time, then I will take a look at the chat, okay. Hi Naveen, hello. Okay, so yes, so let's continue now. So this is the next problem. This is the next one. So here are two identical charges. Identical charges mean they have the same magnitude, okay. So just take them as Q and Q. Just take the two charges as Q and Q. So in the first case, when they were separated by 10 centimeter, the force was 18 Newton. So we can write 18 Newton is equal to K Q square. Q into Q is Q square divided by 10 centimeter square. K Q square by R square, right? In the second case, they're asking the new force. So let's call it as F. So F will be, charge is still the same, but the separation is increased to 20 centimeter. So the new separation is 20 centimeter. Okay. So now it's straightforward. You just divide these two. So F divided by 18 will be this, these two cancel out. It will be 10 by 20, right? 10 by 20 the whole square. So this F will be 1 by 4, sorry, 18 by 4. So 18 by, so this is 9 by 2, 4.5 Newton. Okay. Another way is you can use proportionality. We know the force is directly proportional to or inversely proportional to R square. So if you double the distance between them, the force will become 1/4. Okay, if R is made 2R, then the force will become 1/2 square times the original force, which is F/4, right? So if denominator is increased by 2 times, 2 square is 4, right? So the force will become 1/4. That way also you can do. So the new force, if the separation is doubled, the force decreases by 1/4. So 18/4. But in board exams, you will have to write it step by step like this. Okay. You will also have to write down the diagram and maybe some text also, right? Maybe some extra steps also. Depends on the amount of marks for the question. Okay, so that is basically Coulomb's law when we have two charges. Okay. Now we will talk about how to apply Coulomb's law when we have more than two charges. Okay. When we have more than two charges. So we can just take an example to understand this. Yeah, we will take this example to understand this. So imagine there is a square and 4 equal charges are placed at the 4 corners. So this is A, B, C, D. Okay, this is A, B, C, D. Okay, and in all these corners we have a Q charge kept. At the corners of the square we have Q charge kept. Length of the square is A. Okay, the length of the square is A, side length of the square. They're asking the magnitude of the force on charge B. So here if you observe, there are more than two charges, right? There is 1, 2, 3 and 4 charges. So here how do we find the force? We need to find the force on this Q charge. On this Q charge. So the method is simple. You find the force due to on this Q due to these three separately. So if I only focus on this charge over here, okay, if I only focus on this charge, then this charge will repel this Q, right? So it will exert a force downwards like this. Okay, this is the force due to C. So if I call this as F due to C, what will the magnitude be? K Q1 Q2 divided by A square, right? This distance is A, so this divided by A square. Or we can say K Q square by A square. This is K Q square by A square. So that is going to be this force. Then the exact same force this A charge will also exert, okay, and that will be exerted to the right. Okay, this A charge will repel this Q in this direction. This will be the force due to A. Okay, so we wrote down the force due to two charges. Now only this guy is left. Only this guy is left. So due to D, first you have to connect D and Q with each other. Okay, let me connect it this way. D will repel Q in this direction along this dotted line. So D will repel Q, this Q in this direction. Okay. So this is the force of repulsion due to A, so which I am calling it as Fa. This is the force of repulsion due to C, which I am calling it as Fc. And this is the force of repulsion due to D, which I am calling Fd. Now, if you want the net force on charge B, this is charge B. If you want the net force on charge B, you just have to add A, C and D vectorially. You just have to add FA, FD and FC as vectors, okay, as three different vectors. If you add them like vectors, if you add these three forces like vectors, then you will get the total force experienced by this charge placed here, okay. So what is FA? FA is also KQ square by A square, right, which is basically this value itself. So this is actually also equal to FA, but FD will be different, okay. FD will be different. FD will be KQ square, KQ1 Q2 divided by, what is this distance? This is the diagonal of a square, right, which is root 2a. Diagonal of a square will be root 2a. So now the new distance is root 2a the whole square, which will be KQ square by 2a square. KQ square by 2a square. So what we can do is this KQ square by a square, we can write it as some constant. Let's call it f, okay. Then if KQ square by a square is f, this is f by 2. This will be f by 2. Now let's draw this diagram once again. If this is B, if this is the point B, then we have three forces here. FA, which we can call it as F, FC, which is in this direction, which also we can call it as F. This is also F, this is also F. And the third force, which is FD, which is actually F by 2 in this direction. So we have these three forces that we need to add. So this is actually not that hard to add because these two angles are 45 degree. These two angles are 45 degree, right? So if you look at this F and F, these two blue vectors, what will be the resultant of these two vectors? These two vectors F and F, its resultant will be root 2F in this purple vector's direction. The 2F and F, its magnitude will be root 2F along the diagonal, okay. So this root 2F, and on top of that we have the F by 2. What is the sum now? The sum will be F by 2 plus root 2F. This will be the total force, F net. This will be the total force. Okay, these two blue vectors will result into a root 2F along this purple line. That root 2F plus the original F by 2 will be root 2F plus F by 2. Now you simply add them up. The question is done. So if you take F common, it will be half plus root 2. So just take LCM. Okay, it will be this. And now just check which option matches. I guess it is option C. Right, so it will be option C. So here your concepts of vector addition is important, but the electrostatics idea is simple. You find the individual forces that the charge over here will feel and just add them like vectors, okay, just add them like vectors. Let's take a look at some another question. Let's take a look at this question. So here we have three charges that are placed on a straight line as shown. Okay, so these three charges are placed on a straight line. Distance between adjacent charges is 20 centimeter. We have to find the net force on the middle charge. Okay, so let's draw the diagram. So we have a straight line, and on this straight line we have a 2 microcoulomb here and a 1 microcoulomb in the middle and a 3 microcoulomb at the right end. And the distance between these two is 20 centimeter, and the distance between these two is also 20 centimeter. The question is asking us find the net force on the middle charge. Okay, net force on the middle charge. So this middle charge will feel a force due to this 2 and due to this 3. Okay, so we'll look at them separately. So due to this 2 microcoulomb, it will feel a repulsion force to the right. Okay, let's call it F1. So what will F1 be? Use Coulomb's law. K. So I'm just going to substitute it. 9 into 10 raised to 9. Q1, Q2. So 1 microcoulomb into 2 microcoulomb, which will be 2 into 10 raised to minus 12. Divided by distance between them is 20 centimeter, which is 0.2 meters, right? We can also write 20 centimeter. If you divide it by 100, it is 1 by 5. So 1 by 5 square. So this will be 25 into 2 is 50, 50 into 9, right? So 450, I guess. 450 into 10 raised to minus 3, which is 0.45 Newton. Okay, 0.45 Newton is the force that 2 microcoulomb exerts on 1 microcoulomb, and it will be on the right direction. That is the first force. Then 3 microcoulomb will repel 1 microcoulomb to the left, right? 3 microcoulomb will push 1 microcoulomb to the left, and this force, let's call it F2. So what will F2 be? F2 will be basically the only difference is instead of 2 here, if you do Q1, Q2, it will be 3, right? That's the only difference. So here we'll have a 3. That's the only difference. So 9 into 10 raised to 9 into 3 into 10 raised to minus 12 divided by 1 by 5 square. Okay. So I'll just use a calculator for this. So this is coming out to be 0.675. Okay. This, if you do the calculation, comes out to be 0.675 Newton. So F2 is 0.675 to the left and F1 is 0.45 to the right. So who wins? Of course, F2 is bigger, right? F2 is bigger, so it will win. So the net force is to the left. The net force is to the left, and its magnitude is the subtraction of these two, right? 0.675 minus 0.45. Okay, so what does this come out to be? 0.225, right? Yes. So I guess that should be clear. This is also just vector addition itself, 0.225 Newton. Okay, so your vectors should be clear for this. Okay. The electrostatics concept is simple. You find the force on this pair separately, that is F1, and then you find the force on this pair, which is F2, separately. So the middle charge, it will feel this force and this force simultaneously. And if you want the total force, find their vector sum. Okay, that will be 0.225 Newton to the left. Okay. Okay, so now we will start with electric field. Okay. So electric field is just, you can say an extended idea from the electric force itself. Okay, electric field, you can say it's a different way to look at how charges exert force on each other or interact with each other. So the idea of the electric field is that if I take a plus q charge, okay, the idea of the electric field is that this plus q charge modifies the space around this plus q charge. Okay, when you just keep a plus q charge, it modifies the space around this charge and it generates what is called as an electric field. Okay, this plus q charge generates its own electric field what is known as electric field around in space, around the space. Okay, and it's because of this electric field. Now in this electric field, okay, so the space around this plus q charge is now having an electric field. Now in this electric field, if I place another charge, let's say small q, it will experience a force. Okay, so when we first bring a plus capital Q charge, it generates an electric field around it, and in this electric field, if we bring another charge q, it experiences a force. Okay, so this electric field is just another view or another method to look at how charges interact, okay, electrostatically. So electric field, how it is defined is, at any point we mainly keep a main charge known as the source charge. Okay, and let's say I want to find the electric field due to this plus q charge at this location. Let's call this location as location P, and this location P is at an r distance from capital Q. Okay, so I'll draw it in this page. So we have a plus q charge and I want to find the field, the electric field due to this plus q charge at a location r distance away. Okay, so what I'll do is, the method to find the electric field at any point P is, you place another charge at that location. Okay, and in this case I'm saying I'm placing a q charge. Okay, now we know that because this q charge is in the electric field of plus q, it will experience a force. And what is the direction of that force? That is given to us by Coulomb's law, right? That force is in this direction. And this force we can easily find. This force will be simply the Coulomb formula, K capital Q small q divided by r square. Okay, then the electric field at that point due to capital Q, it is simply the force felt by this q divided by q. Okay, so you can define the electric field at any location as the force divided by the charge placed at that location. Okay, so this just turns out to be kq divided by r square. This is the magnitude of the electric force, sorry, electric field at the point P. Now you can get the q charge away, take the q charge away, and you can say due to this plus q charge at a distance r away, its electric field is in this direction, same direction as the force, and its magnitude is kq divided by r square. Okay, so we use the charge to find the force, and then we do force divided by the charge. Okay, that is the definition of the electric field. The force felt by the q charge divided by the magnitude of that charge. That is how we find the electric field at any point. So electric field due to a point charge if you have a plus q charge, then due to the plus q charge at any point r away, the electric field you can write it as kq by r square. Okay. So I'm not going into that much detail because this is a one shot lecture. Okay. So I'm just trying to cover everything briefly. Another thing is the opposite of this. Okay. Another thing is the opposite of this. So this is, of course, this you can also write as a vector. Okay. Electric field, this you can also write it in terms of vectors. E vector is equal to F vector by Q vector. Okay. Electric field vector's direction is the same as the force direction. Electric field is also a vector itself. The opposite case where, so we wrote E vector as the force divided by the charge, right? Similarly, if at some point P, the electric field is given, at some point P, if the electric field is given, and if I brought another charge Q and placed it in this point, okay, then the force that this Q will feel, the Q charge will feel a force along the electric field, okay. The Q charge will feel a force along the electric field. That force I can get it as Q into E, just multiply Q to the other side. The force that this Q charge will feel, I can write it as Q into E vector. Q into E vector. Okay, so if at some point you know the electric field vector, and if you place another charge at that point, then that charge will feel a force. Okay, that force is given by Q into that electric field vector. Okay, now so that is the simple idea of the electric field. Then, yeah, what is the unit of electric field? The unit of electric field will be, so electric field was force by charge, right? Force by the charge. So force unit is Newton, charge unit is Coulomb, so it is Newton per Coulomb. Okay, there is another unit, volt per meter. This we'll see in the next chapter. Okay, so that is it. That is all. I have some extra text for you guys to read after the lecture. Then this electric field line is also important. Electric field line pattern. What is an electric field line? So we know that if I have a plus Q charge at any location, in the space surrounding this plus Q charge, it will exert an electric field. There will be an electric field everywhere, right? So if I choose a random point, let's say over here, how will I find the direction of the electric field? I will place a Q charge here and see where it experiences the force. And that is easy. It will experience a force in this direction. It will experience a repulsive force in this direction. This is also the direction of the electric field. Okay, at this point. Now you can remove this Q. So that is how you find the direction of field. So if you can imagine putting a plus Q charge there. So it will feel a force here, right? So this is the direction of the field. Similarly, if you place a plus Q charge here, it will feel a force in this direction, in the upward direction. Okay, so at this location, the field is in this direction. Okay, and what about here? Here it will feel a force in this direction. So at this location, the field is in this direction. So that is how you find the direction of the field. You assume a positive charge at that point and see which direction is the force pointing. That is the direction of the electric field. So for the positive charge, if we have a plus Q charge, okay, then its field line pattern will be radially outwards. क्या was it? Huh? Okay. Okay. Okay, so for the positive charge, this field line pattern is important. It is radially outward. Okay, the arrows are pointing outward, and it is showing the direction of the electric field. Okay, for the negative charge, it's the opposite. It is radially inward. Why is it radially inward? Because if I place a, how do we find the electric field? We place a positive charge at that point, right? We keep a positive charge at that point. Now this negative charge will attract the positive charge. That's why the field is in this direction. Similarly, if you place the positive charge here, it will be attracted in this direction. So that is why the field direction is in this direction. So for a positive charge, it is radially outward lines, and for the negative charge, it is radially inward line for the electric field. Okay, so these line patterns can be asked for the positive or the negative. So now we will try out a question. So in this question, an electron falls through a distance d in a uniform electric field. Okay, so uniform means constant always. Uniform always means constant, and electric field's magnitude is given as E. The direction of the electric field is then reversed. So first, let's talk about the first question. They're asking find the time of fall in each case. So first, let's talk about this case. Okay, first let's talk about this case. So if we have a charge in an electric field, we just learned it here. If you place a positive charge in an electric field, it will experience a force in the direction of the electric field. But if you place a negative charge, a minus Q charge in an electric field, it will experience a force opposite to the electric field. Okay, negative charge will experience a force opposite to the electric field. Okay, so electric field is the direction in which a positive charge will feel a force. So if you place a positive charge in an electric field, the force will be in the direction of the electric field. And if you place a negative charge in an electric field, the force will be opposite to the electric field. Okay. Now in the first question, we have an electron placed in an electric field. Okay. So these blue lines that they are showing is the electric field. And they have said that it is constant. Okay. They have said the electric field is constant. So if the electric field is constant and if we throw an electron inside, electron is a negatively charged particle, right? So what will be the direction of force? Electric field is upwards, right? Electric field of E is acting upwards. So the force on the electron will be downwards because it's a negative charge. The force on the electron will be downwards. And this force is given by the charge into electric field. Charge on the electron is small e, electric field is capital E. That will give us the force on the electron. Also notice that this is a constant force, right? This is a constant force because electric field is constant, right? So it's a constant force. So if I know the force, I can find the acceleration as well. The acceleration will also be in the direction of the force itself. And that acceleration is given by force divided by mass, Newton's second law, right? So force is E into capital E divided by the mass of the electron. This is the acceleration of the electron, okay? The acceleration that the electron experiences. Now it has to fall through a distance d, okay? Electron falls through a distance d. And let's say it starts, okay, it starts to fall, right? So let's say it starts from rest. So the electron is starting from rest and it is falling by a distance of d. So what is the time taken for this? So this is just a standard result as well. This will be root 2h by g if you guys remember from gravity. free fall equations, or you can just use S equals ut plus half at square. So the displacement is actually d. It will be half into acceleration into t square. Okay, now this time, this t will give you the time taken by the electron to fall downwards. Okay, it will give you the time taken by the electron to fall downwards. Now in the second question they are saying there is a proton. Okay, in the second question they are saying electric field is then reversed. Okay, but now we have a proton falling through it. Okay, now for the proton, it is a positively charged particle, right? So the force will be in the direction of the field. Field is also downwards. So the force will be E into E itself downwards. Okay. So proton or electron, the force is the same. The force will be the same. But the acceleration is not same. Acceleration of the electron was the E into E divided by me, right? But acceleration of proton will be different because mass of the proton is different. Mass of the proton is different. So in fact, proton is like 1800 times heavier. So mass of the proton is approximately 1.67 into 10 raised to minus 27 kilograms. So proton is significantly heavier than the electron. Okay. So the acceleration of proton is different, but everything else is the same. Okay. So if this is the time taken by the electron, which I am calling it as T1, time taken by proton, you can use the same equation. D is equal to half. Acceleration is EE by m into T2 square, half AT square. Okay, so now if you want to compare the time, you can just divide these two, right? So basically we can say T2 square by T1 square equal to MP divided by ME. So if you divide these two equations, you will get this relation, right? Yes, you will get this relation. And from here you can compare the time. T2 by T1 will be square root of mass of proton divided by mass of electron. Okay, so the time ratio T2 by T1 is equal to root of MP by ME. So the main logic is that proton's mass is different, okay, but charge is the same. Their charge is identical in magnitude. So because their charge is the same, the force on them is the same. The force will be E into E, right? But the mass being different changes the acceleration. Okay, so that is the main idea in this question. Okay, after that it is just the free fall equation. S is equal to half AT square. Okay, S is equal to half AT square. Okay, so now how do we write electric field due to multiple charges? It's the same way we learned for the forces. Okay, if you want the net field due to multiple charges, you find them individually and add them vectorially. Okay, we'll do a question to understand this. It's the same method we did for the forces. So if we take this question, 2 point charges plus q and minus q, I'll draw that diagram. So if we take two charges of plus capital Q and minus Q, okay, if I take two charges like this, they're placed 2a distance apart. So the distance between them is 2a. We have to calculate the field at A, B and C. Okay, so I guess the points A, B and C are, one point was the middle point. Okay, let's call this as A. The other point was a distance to the left. Let's call this as B. And then yes, so we have something like this. This is the third point, which we can call it as C. So we will have to find the electric field at these 3 points, A, B and C, and this distance is also given. Okay, so firstly, what is the electric field due to a plus Q charge that we just discussed? At a distance r, it will be in this direction along the r direction, and its magnitude is kq divided by r square, right? Due to a minus q charge, the only difference is the sign, sorry, the direction. It will be radially inwards. The electric field will be radially inwards. Magnitude is still the same, kq by r square. Okay, this is how we write the field due to a plus q charge and a minus q charge. Now let's say we want first the field at A, okay, at this location. First ignore minus q and just take a look at plus q. So the field will be in this direction. So let's call it F plus, not F, E, E plus. So E plus will be kq divided by a square, right? Because this distance is a distance away. And E minus, so the due to the minus charge, the field will be radially inward. So it will also be to the right. This is the electric field due to the negative charge, right? So E minus, E plus is to the right. E minus, its magnitude is kq by a square. And this is also pointing in the right direction. So if you want the total field at A, if you want the total field at A, it will be the sum of this and this, right? You need to include the contribution of E plus and E minus. They are both equal to kq by a square. So the net field will be two kq divided by a square. This will be the net field, okay, because they will get added up. Now let's choose the point B. So at the point B, due to E plus, it will be to the left. Magnitude distance is A, so this will be kq divided by a square. And minus will attract, so due to minus, it will be to the right. Okay, but the field is going to be different because the distance from minus q is 3a, right? A plus a plus a, so 3a. So the field here is kq divided by 3a, the whole square. So this is a very tiny contribution, right? Because the minus q is much far away from B, its contribution is very small. So net field at B will be in the left direction. Okay, so let's call it as EB. I'm going to call it as EB. So EB will be this left minus the right. So that will be kq divided by a square minus kq divided by 9a square. Okay, if we have two vectors that are opposite in direction, then their resultant is you have to subtract them, right? So this left direction force, you have to subtract it from the right direction force or field. So this will be 8 by 9, I guess. 8 by 9 kq by a square. This is the field at point B. Now we need to find the field at point C. Okay. All right. Now, how do we find the electric field at this point C? Same logic, but here it will be slightly different, slightly more complicated. Okay, these distances are given. Okay, so using this distance, we can find out this angle. Okay, this is actually just an equilateral triangle, right? 2A, 2A, 2A. This is an equilateral triangle. So all the angles are 60, 60, 60, and this is also 60, which means this angle over here is half of it, 30. This is also 30. Okay, so now due to this plus q, the field will be along this blue line. Due to this plus q, it will be along this blue line like this. Let's also extend this line. Okay, so due to this plus q, it will be along this yellow line, the electric field. And what will be the magnitude? The magnitude will be kq divided by 2a, the whole square, right? Distance of the point from the charge is 2a, so it will be kq by 2a square. Similarly, for the negative charge also, the magnitude will be the same because the distance is 2a. But for the negative charge, the direction will be along this blue line towards q, minus q, because due to negative charges, field is attractive. So the field direction will be towards this minus q. Now, so if I draw a horizontal line here, okay, then I can say, so if this angle is 30, this angle will also be 30, okay. So this is vertical, this is the horizontal, so this angle is 60. Similarly, this is 30, so this will also be 60, okay. So these two magnitudes are equal, right? The magnitude of this field, if I call it as E, let's take both of them as E itself. So magnitude of this is also E, purple arrow is also E, and this yellow arrow is also E. So it is easy to see that the y component is E cos E sin 60, and here the y component is minus E sin 60. So their y components cancel out. So the net field will be along the x direction. Okay, their net field will be along the x direction. Okay, because their y components cancel out, so only their x components will survive, and you can just add their x components. So x component due to this yellow arrow will be E cos 60, and x component due to this E vector will also be E cos 60, so plus E cos 60. Cos 60 is half, so this will simply be E by 2 plus E by 2 is E. So what is E? Kq divided by 2a the whole square, which is 4a square. So this will be the answer for electric field at C. This will be the answer for electric field at this point C. Okay. So for electric field, you just have to use vectors, okay, and carefully look at their components. All right. resultant, yes. Yes, this is for boards. Sitara, this is for boards. Okay. This is mainly for boards only. So now we'll take a look at some electric field derivations. Okay. So now we will do some integration. So the first charge distribution that we'll be looking at is a semi-ring. Okay, a semicircular ring or a semicircular wire carrying uniform charge. Okay, this is the first charge distribution we'll be looking at. In fact, let's just derive it for the semicircular arc. Okay, let's just derive it for the semicircular arc. I think I don't have that diagram, so I'll derive it here. Okay guys, I drew a full circle, but it's only an arc. I'll try to remove this part. So due to this arc of a circle, we need to find the electric field at the center. Okay, that is the first exercise first derivation we'll be doing. So on this arc, we have a uniform charge distribution. We have positive charge uniformly distributed. And we need to find the field here. Okay. Okay, we need to find the field here. So here the main logic is, I'm going to draw the angle bisector. Angle bisector is that line which cuts the angle into two halves. Okay, and this angle, let's call it as alpha. This full angle, I'm going to call it as alpha. Okay, so now I'm going to discuss a point. Okay, I'm going to prove that the field due to this red arc will be along this green line. Okay, I'm going to prove that. So to notice that, what I'll do is I'll take an element. So this is the angle bisector line. I'll go clockwise by some angle theta. Okay, and at this location I am choosing a small dq charge. Dq in calculus means a very small quantity. So I'm choosing a very small quantity of charge here, which we can practically treat it as a point charge. Okay, then if I ask you to write the field due to this dq, it will be along this purple line. So just extend it down. It will be along this purple line. Okay, and if this angle is theta, this angle will also be theta. Okay, and because this is a very tiny charge, I'm going to call this as a very tiny field, dE. Now symmetrically, if I go theta angle on the other side, it will look something like this. And I take a same dq charged piece over here, then the field due to this guy will be in just a second. The field due to the other dq will be in a direction like this. Okay, basically opposite to this purple line. Let me see, something like this. Okay, and this will also make the same angle theta. These two angles will be theta theta. So if what I did is I went theta angle on either side of the angle bisector and took two dq pieces and wrote down their electric field, okay, which is dE. I'm calling this electric field as dE. Now what are you observing? So if you notice something, dE's component along the green line is dE cos theta, and dE's component along the green line, the other dE's component along the green line is also dE cos theta. But if you notice the perpendicular component of this dE, it is dE sin theta, and the perpendicular component of this dE is dE sin theta itself, but on the other side. So these two cancel each other out. So only the component along this green line survives. Only the component dE cos theta survives. Okay. So which means if I take 2 dq on the arc, the net field is coming out to be along the green line. Hence we can say that the field due to the whole arc will be along this green line itself. Okay. So that is the logic I'll be using. So now all I have to do is, if this is the arc, as I have observed that the field will be along the angle bisector, now I'll start the integration process. Okay. So I'll go a distance, I'll go an angle of theta clockwise. Okay. And I'll take a very tiny angle of d theta as well. I'll go forward a very tiny angle of d theta. And I'll take this element between these two lines. Okay. What is the length of this tiny length? dl. So the radius of the circle, if it is r, the length of this segment is r into d theta, right? This angle is d theta, so this length will be r d theta. Now this r d theta, we will consider it as a point charge. So the field will be, write down the field due to that charge. The field will be in this direction. Field will be in this direction. And I'm saying this is equal to, so this angle will be theta. This is going to be the small dE due to r d theta. This is the field due to r d theta. So can I write this dE? dE will be, so treat this like a point charge and write the field at this point. So this distance of the charge from the point P is equal to radius of the circle. Formula is kq by r square, right? So the charge, if I call it as dq, so k dq divided by radius square. This will be the magnitude of electric field at this point P. Now how do we write this dq? So basically this is a uniformly charged arc, right? So let's say the charge per unit length is lambda. So if I say lambda is the charge per unit length, if I say lambda is the charge per unit length, I can say the charge of this length r d theta is actually lambda, which is the charge per unit length, into the length. Length is r d theta. So this dq, I can write it as lambda r d theta. So this will be k, and instead of dq, we will write lambda r d theta divided by r square. So this will be k lambda divided by r into d theta. This will be the small electric field at the point P. Okay. But we are not done yet. We know that the net field is in this direction. right, along the angle bisector. This is the direction of the net field. So all I have to do is I have to integrate this component. Okay, what is this component along the green line? dE cos theta. So if I want the net field, all I have to do is integrate dE cos theta. dE was k lambda by r into d theta into cos theta. Okay, so from here k lambda by r is a constant, so take it outside the integration, and we'll need cos theta d theta integration. Now all that is left is the limits of theta. Okay, now theta, we took it, the positive direction of theta, we took it as clockwise. Okay, so for the circular arc, if the angle, if this is the angle bisector, both these angles are alpha by 2 for the full circular arc. Okay, so the limits of theta will be from here, which is the leftmost end. Here theta is equal to minus alpha by 2 till the rightmost end, which is theta equal to plus alpha by 2. Okay, we take clockwise theta to be positive. So this point, at this point, the value of theta is plus alpha by 2. And at the opposite end, the value of theta is minus alpha by 2, because this is an anti-clockwise angle. So the limits will be from minus alpha by 2 to plus alpha by 2. So this turns out to be, what is the integration of cos theta? It will be sin theta. Limits are from minus alpha by 2 to plus alpha by 2. So I guess this will be 2k lambda by r sin alpha by 2. Okay, the formula is more important. Okay, 2k lambda by r sin alpha by 2. So basically, if I have to summarize this result, if I have a circular arc which subtends an angle alpha at the center, and this is the angle bisector, then the field here will be along this angle bisector. That's the first thing. And the magnitude is given by 2k lambda by r sin alpha by 2. Okay, so this magnitude is the second thing. Lambda is the charge per unit length. Okay, so if we use this formula, we can get the answer for the semicircular arc as well as a quarter circle, right? For a semicircular wire, all you have to do is put this angle alpha as 180 degree. Put this angle alpha as 180 degree, right? So the angle bisector is going to be in this direction. So field is in this direction. And the electric field value will be, if you put alpha as 180, sin 180 by 2, sin 90. So this will be 2k lambda by r. It will be 2k lambda by r. Okay, and for the quarter circle also you can find. Okay, for the quarter circle you will have to put alpha as 90 degree. Okay, so this derivation, I know it is kind of hard. Okay, So now this is more important for your board exams, the uniformly charged ring. So here we have a uniformly charged ring, the same lambda charge per unit length, okay, and from the center of this circular arc we are going a distance x to the right, and we want to find the field at this point P, okay. We want to find the field at this point P. So for this, what we do is we once again choose a small tiny element on the circumference. I am calling it as dq, and due to this dq I will write the field at this point P, okay. That is easy. Due to a point charge, first connect a line to the point and the field will be along that line, okay. So this will be the electric field dE. Now if I call this angle as theta, the component along P, along the axis, will be dE cos theta, and in this direction it will be dE sin theta, right. Now the thing is, if I choose another dq exactly below over here, if I choose another dq exactly below over here, just like the dq on the top, here the electric field will be in this direction, right. Here the electric field will be in this direction. Similarly, if this angle is theta, this will also be theta. And even for this dq, this component will be dE sin theta. So as you can see, these dE sin theta components, they cancel out if you take all the elements. If you take two dq's together, the dE sin theta cancel out and only the dE cos theta is getting added up. So by noticing that, the first thing you should understand is, if you have a circular ring at the point P, there will only be a component along the axis, okay. There will only be a component of the field along the axis. So the net field will be along the axis. The perpendicular ones cancel out, okay. And we demonstrated by taking two dq charges, and we saw that the dE sin thetas get cancelled out. So only the dE cos theta survives, which means the net field will be in the direction of the axis. Now all you have to do is integrate this component, okay. If you integrate this component, you will get the answer. So the net electric field will be integration of dE cos theta. So what is dE? dE is kq divided by this distance square, okay. So the radius is taken as capital R, this distance is taken as x. So I'll call this hypotenuse for some time as small r, okay. So dE I can write it as k dq divided by small r square, okay. And cos theta is x divided by small r, right. Cos theta is x divided by small r. So this will be k into x into dq divided by r cube. This is the electric field. We have to integrate this. But actually this integration is very easy to solve. There is no integration involved, because this x distance is a constant, right. X is the distance of this point P from the center of the circle. That is a constant. So this is a constant. R is also a constant, small r. So the only thing that is a variable is dq. So you can take all constants outside the integral. So kx by r cube, you can take it outside, and inside you will have integration dq, okay. Now integration dq means add up all the dq charges on the ring, okay. So in the circumference, basically add up all these charges that are present on the circumference. That is what integration dq means. Okay, integration just means to sum up. So you have to sum up all the charges on the circumference. So that will come out to be capital Q. Okay. So finally the formula is K capital Q x divided by R cube. This is the formula. Okay. So to summarize, for this circular ring, at a point which is at distance x, firstly the field is in this direction along the axis, and the magnitude is given by kqx divided by r cube. Okay, this r is not the radius. Okay, radius is actually this one, capital R. This is your small r. Okay, now in NCERT you will see a different form. In NCERT you won't see r but r square plus x square, right? So basically r square you can write it as capital R square plus x square using Pythagoras, right? So r will be simply under root of r square plus x square, which is r square plus x square raised to power half. This is what small r will be. So this you will have to substitute here, which is kqx divided by r square plus x square raised to power 3 divided by 2. Okay, small r will have a half power, but that needs to be cubed, so it will be 3 by 2. So this will be the formula. Okay, in the case of a ring. So if you have a ring uniformly charged with plus q charge at a distance x on the axis, this is the formula for finding the field. Okay. Duration, so let me check. It is still 9:30. Okay, duration is still 9:30. Whatever we can cover until then, we will cover. Okay, great. So this formula you can just expect. Okay, like in board exams, if that's your target, then you can pretty much expect this derivation. I guess the previous one would be like a little too hard for board exams. Okay. Then we have this question. A thin plastic rod is bent into a circular ring of radius r. It is uniformly charged with charge density lambda. Okay. Okay, so here they are asking the magnitude of the electric field at the center. Okay, what they are asking is, you have a uniformly charged ring. Okay, you have a uniformly charged ring like this. You have to find the field at the center. Okay, the center of this circle. At the center of this circle. So there are two ways. You can either just put x equal to 0 in this formula, right? So here if you put x equal to 0, right, x equal to 0 means this point is at the center, right? X is the distance of this point P from the center of the circle. So x equal to 0 means this point P is at the center of the circle, right? So if you put x equal to 0 here, you will get the field at the point O. So that field will be 0, right? You can see, you can put x equal to 0, the numerator would become 0, right? So the field is actually 0. Another way to see it is you can take a tiny charge dq over here. Okay. And through a diameter connect it to the opposite point. and here also choose a dq charge. Here also choose a dq charge, similar to this guy. So due to this guy dq, this is the center. Due to this dq, the field will be in the downward direction, k dq by r square, right? And due to this dq, it will be upwards, k dq by r square. So as you can see, it mutually cancels out. Similarly, if you choose two dqs here, such that they are also connected with a diameter, their components will also cancel out. So all of them will mutually cancel out, right? Let's take a dq here and a dq here. So due to the dq on the right, field will be to the left. Due to the dq on the left, field will be to the right, and these two also cancel. So they will all mutually cancel out. Therefore, the field at the center, it will be 0. It will be 0. Okay. So that is this question. Great. This is also a CBSE question itself. Okay, then we have some properties of electric field lines. Okay. So electric field lines, the first thing is the field line is supposed to represent the direction and strength of an electric field. Okay. So basically, if you have a electric field line pattern like this given to you, what this line means is, if you place a small positive charge here, it will experience a force in this direction. It will experience a force in this direction. Similarly, if you place the charge here, it will experience the force in this direction. Okay, what about here? It will be experience a force in this direction. Okay, so electric field pattern, it tells us about the direction of the electric field. So if you place a positive charge here, it will feel a force in the direction of electric field, right? If you place a positive charge here, it will feel a force in this direction. So that is what electric field line tells us about. It tells us about the direction of the electric field. That's the first point. Okay. Then the tangent to the electric field line at any point gives the direction of the electric field at that point. So this point, what this means is, let me take the example of a simple electric field line. So I'm saying we have some electric field line that looks like this. Okay, this is some electric field line, and I'm interested in the electric field here at this location. So all I have to do is draw a tangent to this line at this point P. That will be in this direction. This is going to be the direction of the electric field. Okay, this is going to be the direction of an electric field. Okay, so if you place a plus Q charge exactly at this location, it will feel a force in this direction. Okay, so if you have some curved field line like this and you need the field at some point, then all you have to do is draw a tangent to that point. Okay, the tangent will give the direction of the field. So that is the second point. Okay, now the third point is, field lines originate from a positive charge and terminate on a negative charge, or at infinity if no opposite charge is present. So this we kind of already saw earlier. Oh, so in the positive charge, as you can see, just for the positive charge, the field lines, it originate from the positive charge, right? The lines are originating from the positive charge, but there is no negative charge to terminate on, right? So it goes off to infinity, right? But it is originating from the positive charge. So whenever you see a positive charge, it will always be a source of electric lines, electric field lines, which means lines will originate from the positive charge. And for the negative charge, field lines will always terminate on the negative charge. Okay. Field lines, as you can see, are terminating on minus q charge, right? So negative charge, field lines will terminate, and positive charge, field lines will originate. Okay. So that was the third point. We will see another field line pattern after some time, and there also we will see this fact. Then closer field lines indicate a stronger electric field, while widely spaced field lines indicate a weaker field. So this example basically tells us about that fact. So here we have field lines that move like this. Okay. So at this location A, close to A, we have field lines that are crowded together, right? So near A, as you can observe, field lines are more crowded. Field lines are crowded as compared to B. Near B, the field lines are more spaced. So that spacing tells us about how strong the electric field is. So where the field is crowded, like near A, the field lines are crowded, it means the field there is stronger. Okay. So more crowding, stronger field. Okay. That's why the field at A is stronger than the field at B. Okay. Another example could be something like this. Okay, we can have a field pattern like this. So if I have to compare field at this location, A versus this location, it is easy to say that at B there is more crowding. So field here is bigger than field at A. So EB will be greater than EA. Because it is here there is more electric field present close to each other. Here the fields are far away. Okay, so the density of field lines, how close they are packed, tells us about how strong the field is. Okay, then that is this point. For a positive point charge, okay, this we already saw. Okay, this we already saw. Yeah, so the last one is also the same. Then there is a few more important facts. Okay, the one fact is that any two field lines, they cannot intersect. Okay, this is just common sense, because if you look at line number 1 here, if you want to locate the field, you will draw a tangent, right? This is the electric field at point P. But on line 2, if you draw the tangent, it will be in this direction. But this is not possible, right? At any one point, if you choose any one point, there can only be one field. Electric field can only point in one direction. But this is telling us two different directions, which is impossible, okay? That's why electric field lines, whenever they give you a diagram, they will never intersect with each other, okay? They will never intersect. Then, yeah, we can take a look at this now. So here we have a diagram of two positive Q charges, okay? Two plus charges. The field pattern due to this is also kind of important, okay? But here you can see all those facts we just covered. From this plus charge, field lines will originate, okay? They will start from this, as you can see. From a plus charge, field lines will always originate, okay? As you can see. From here also, as it is a plus charge, it will originate. And and at the middle, at this location, there are no field lines, because here field is 0. Okay, why is the field in the middle 0? That is easy to observe. If you have two plus q charges, then the field in the middle will be 0, right? Due to the charge on the left, field is to the right, kq by a square. And due to the charge on the right, field is to the left, kq by a square. The field cancels out. Okay. So if you have two equal charges like this, field here is 0. That's why there is no line here. Okay. So what happens is they will kind of become parallel over here and go to infinity. So there will be a symmetry about this axis, as you can see. There is a symmetry about this axis. This is how pattern of two positive q charges look like. And this is actually what we call as a dipole when we have a plus q and a minus q. Okay. Here story is slightly different. Here field lines will originate from the positive and terminate on the second. Right? Negative charges, fields will terminate on them. So here also, as you can see, this field line also follows the same pattern. Here also it follows the same pattern. This will also do the same like this, but it goes much further away. This line will also do the same. Okay, and you guys get the idea. So these field patterns are also important. Okay. Yeah, so that is it. This is the two positive charge. That is the plus q and the minus q one, dipole one. Yes. So in that question, Sitare, everything will cancel out. Okay. All right. So now, oh yeah. So there was this one more point, which is electric field lines, right? Electrostatic field lines. They never form closed loops. Okay, because the electric field is something known as a conservative field, like the gravitational field. So this is something that we cover in work power energy. So the electric field is a conservative field. Like the gravitational field. So it will never form a closed loop. You cannot have a field line pattern like this, which is like a closed loop. This is impossible. Okay. This is impossible. So it's the same rule for gravitational field also. You won't see any gravitational field pattern following a closed loop as well. So this is also asked. Okay. So now, yeah, so this question is based on that. This one question is based on that idea. Which of the following statements is correct? So electric field due to static charges, right, is conservative. That is true. And field lines do not form closed loops. This is also true. So A option is correct. So everything else is wrong, right? Any field that is conservative cannot form closed loops. Okay. So this is something that we cover in work power energy. There we talk about conservative forces. So one rule of conservative forces is they do not, the work done in a closed loop is 0. Okay. So right now, just remember that electric field or gravitational field cannot have a closed loop pattern like this. cannot form a closed loop pattern like this. Okay, of course, this is the direction. This is impossible. Okay. Then, so now there is this concept of null point. Okay. So null point just means zero electric field. So I'll take an example to explain this. Let's say we have a charge of Q and 4Q, and it is said that at some point in between this Q and 4Q, the field is 0. Okay, we have to find where is it 0. So we can kind of imagine that 4Q is the bigger charge, so this guy's free field will be stronger, so it will be somewhere over here, right? So 4Q's field, let's say it is E to the left, and we want Q's field to be E to the left as well, right as well, so that they cancel out, right? That is the logic. If I want 0 net field at the center, if I want 0 field at this point P, then the field due to Q and 4Q should be 0. I don't know where this point is, so I'm calling this as X. Okay, and this total distance will also be given. Let's call it as D. So if the distance of Q and P is X, then this distance will be D minus X. This distance will be D minus X. Now you can apply the formula. Due to Q, field will be KQ by X square, and due to 4Q, the field will be leftwards, and magnitude is K into 4Q divided by D minus X the whole square. Divided by D minus X the whole square. Now for null point, what that means is the field here is 0. We want the net field at point P to be 0. That means these two must cancel each other out, right? So we can say KQ by X square is equal to this thing. So we can say left KQ by X square is equal to K into 4Q divided by D minus X the whole square. The field to the left is equal to field to the right. So now cancel out KQ. Take D minus X the whole square here. Now take square root. So this will be D minus X divided by X. Okay, left side. Square root of 4 is 2. 2x plus x is equal to D, which means x is equal to D by 3. So the point where the field is 0 is actually D by 3. So if this is Q and this is 4Q, then the point where the field is 0 is over here somewhere, such that this is D by 3. Okay, so of course this will be 2D by 3. So that is how you find the null point where the field is 0. This is where the field is 0. Okay, so questions like this can also be asked. If they were both equal charges, then it is easy. The null point will be at the center, at the middle, right? So that is the idea of null point. So So we had electric flux and Gauss law as well, but we'll just do dipole today. Okay, we'll just do electric dipole today because flux and Gauss law will need some more time, right? So we'll just finish it off with dipole. Electric field is a vector itself, but we can use common sense to find the direction, right? what I mean is, in that question, right, we had a Q charge here. So, and if I want the field here, I can guarantee where the direction is, right? I can easily say, if I want the field direction at this point, I can easily tell it is to the right. E due to Q will be to the right. And due to the 4Q1, the field will be to the left, right? E due to the 4Q will be to the left. So it's just left and right. So that's why I just wrote it down as scalars, right? Because the left direction field magnitude must be equal to right direction field magnitude. Then these two cancel out, right? If you apply, like if I take force example, 3 Newton to the left and 3 Newton to the right, then these cancel each other out, right? Because 3 Newton to the left is and 3 Newton to the right means net force 0. Similarly, EQ and E4Q should balance each other out. Okay. So that's why I just equated their magnitudes. I just simply equated their magnitudes. Okay. All right. So now we'll just quickly do the dipole derivations as well. So electric dipole. So dipole. So that term is basically for classifying the system where we have a point charge, where we have 2 point charges, minus Q and plus Q, and they are separated by some distance. Okay, now in NCERT, this distance, I guess they are taking it as 2a. Okay, but you can take it as d also, it doesn't matter. So, and usually this 2a is a very small distance. Okay, in like these are like in angstrom order, like very, very tiny distances. So we have two charges that are very, very close to each other, very tiny separation apart, and they are equal and opposite charges. This is what we classify. This system is what is called as a dipole. Now in this system, we define a certain vector known as a dipole moment vector, and the direction of this vector is from the negative charge to the positive charge. Okay, and we use the symbol P for this. This is the dipole moment vector. It is always from the negative charge to the positive charge. Okay, and the magnitude of this dipole moment is written as the charge Q into the distance between the two charges. Okay, Q into 2a. And so now we have some formulas for this to derive. First thing is the electric field on the axial line of the dipole. Okay, so dipole is basically just that. It's a system of these two charges. Okay, so in the first case, we have a minus Q charge here and a plus Q charge here. And let's say this is the midline. This is the middle line. And from this middle line, so this distance is A, this distance is also A. Along the axis of the dipole, I want the field at some point P over here due to this dipole. Okay, that is the question. And the distance of the point P from the central line, this distance we know it is R. Okay, this distance is R. So what is the distance from the positive charge? That will be R minus A, right? So this distance will be R minus A, and the distance from the negative charge will be this r plus a. The distance from the negative charge will be r plus a. Now just use common sense to find the direction. Q will exert a rightward field. Q's field will be to the right. So this is the field due to the positive charge. And negative charge will pull P to the left. So negative charge's field will be to the left. Which is stronger? Of course, the field due to the positive charge will be stronger because it is closer to P, right? So E plus will be greater. So which means the net field will be along the right direction. The net field will be along the right direction. Now just solve it. The net field will be this E plus minus this E minus. Okay. Now the field due to this plus Q charge is KQ divided by R minus A the whole square. Just use the point charge formula. And field due to the negative charge is KQ divided by R plus A the whole square. Okay, so now I guess you can take some things common. If you take KQ common and then take LCM also, R plus A the whole square minus R minus A the whole square, right? So that R square A square cancels out and you will get 4RA. Over in the numerator you will get 4RA. Try it out, but you will get 4RA. And in the denominator you will have so R minus A into R plus A, that is R square minus A square. A plus B into A minus B is A square minus B square, and on the outside we have another square, right? So this thing into this thing will be R minus A into R plus A is R square minus A square, and on the outside we have a square. So now at this step we are using an approximation. Okay. So whenever we talk about dipoles, there are two distances, right? R and A. This distance R that we are talking about is significantly bigger than A. Okay, always. So whenever we discuss dipoles, this distance RA is much bigger than A. Okay, which means the actual situation is like this. This is the negative charge, this is the positive charge, and the point we are talking about is here. Okay, this is the actual situation we are talking about. This will be 2A, this is going to be your R. So what we'll do is, if we know R is much bigger than A, then R square will be even bigger than A square, right? So what we can do is, this R square minus A square, in the denominator, we can approximate it as, this is very small, so we can get rid of it, and we can write it as R square. So this denominator will become R square the whole square, which is R raised to 4. So this becomes KQ into 4RA divided by R raised to 4. Okay, divided by R raised to 4. 1 R cancels out, and this becomes K into KQ into 4A divided by R cube. This is what we get. Okay, and here we know the dipole moment's magnitude is 2A into Q. So 2AQ we can write it as P, so this will be 2KP divided by R cube. There will be a 2 left in the numerator, so it will be 2KP divided by R cube. This will be the field at the point P. So if we have a dipole, minus Q plus Q is like this, and from the center of the dipole, if we go a distance R, then on the axis the field, okay, so we calculated the field to be in the right direction, right? And the magnitude is 2 kp divided by r cube. Now here there is another thing to keep in mind. If you notice, the dipole moment vector is also in the right direction, right? And the field is also in the right direction. So in this case, when we are talking about axial position, the field is in the direction of the dipole moment, okay? So you can also write it as 2kp vector by r cube if we are talking about axial positions. So in the axial position, wherever you choose, the field will be in the same direction as dipole, okay? The field will be in the same direction as the dipole moment. Okay, so this is the field on the axial line of the dipole, okay, along the axis. Then yeah, electric potential would be a scalar, right? So that that we'll cover in the potential chapter, but that you can just add them like scalars, right? The potential due to positive charge is kq by r, right? Let's say this is r1, and potential due to negative charge, let's say it is minus kq by r2, and just add them like scalars, okay? In potential, you don't have to pay attention to the sign because they are scalars, right? Potential, electric potential is a scalar. So there is no confusion there. We'll derive that later, okay? Now what is left is for the equatorial line. So equatorial line, we can quickly do it now. Actually, we already did it in a way, right? I guess the old question we did, where was that question? Yeah, this question. This question, if you observe, here we just have a dipole, right? Q and minus Q, and it is at a 2a distance away. Let's see, but it's not exactly the same because this distance is 2a and this is also 2a. That is not exactly the same, but it's going to be similar. It's going to be similar. So equatorial line means basically if this is minus Q, this is the Q point, then draw the perpendicular bisector like this and choose a point on this line. Okay, this is the equatorial line. Let's say this point. So we need to find the field at this point. This length is A, this is also A, and this purple length is R. Okay, once again, R is much bigger than A. So connect these 2 points and these 2 points. So here the field due to the negative charge will be towards the negative charge, right? And the field due to the positive charge will be away from this positive charge, like this. Okay. Now draw the horizontal line here. So here the magnitude will be the same due to both these charges. If you say this distance is d, hypotenuse, so this distance is also d. So this electric field will be kq divided by d square, and this electric field will also be kq divided by d square, same magnitude. Okay, so now let's say this angle, what do we do here? So we'll just say this angle, if it is theta, let's say, this will be 90 minus theta, which means this will be theta. Okay, and yes, and this will also be theta. So these two angles will also be theta. Okay, you can also look at it like this. If this angle is theta, then this angle will also be theta, right? Just look at this Z. So that way also you can do it. So now it's clear that the net field will be in the left direction, right? Kq square by d square, kq square by d square, their sine theta components will cancel out. So only the left direction component is left. So this will be the electric field, net electric field, and that will be kq square by d square. Kq square by d square cos theta plus kq square by d square cos theta. So this will be into 2 cos theta. 2 kq square by d square cos theta will be the field. The y direction cancels out, y direction components, they will cancel out, and only x direction will survive, right? Now what is cos theta in this triangle? Cos theta in this triangle will be a divided by hypotenuse, which is d, a divided by d. So this will be 2 kq square um, 2 kq square into a divided by d cube, right? So now what we can do is this d we can write it as, using Pythagoras, a square plus r square. So denominator will become a square plus r square under root, but there was also a cube, so it will be raised to power 3 by 2. This is the denominator. Okay. Now once again we'll do that trick. 2a into q. 2a into q, we can write it as p. So this will become kp. Numerator will become kp. And we get rid of this a square, neglect it. So we neglect this, approximate it to 0, because a is very small compared to r, right? So r squares under root will make it r, but there is also a cube. So this will become r cube. So this is the electric field magnitude in the axial position. But is it in the direction of the dipole moment or opposite? So dipole moment is pointing to the right, whereas the electric field here is pointing to the left. So you can say it is opposite to the dipole moment. So if you want to write this in vector form, this is the magnitude. If you want to write it in vector form, then E vector you can write it as minus kp vector by r cube. Why is there a negative sign here? Because the electric field is opposite to p vector. That is why we write minus p vector here. Okay. So in the axial case, once again summarizing, if you have the dipole moment like this to the right, draw the axial line, and at any point the field will be opposite to the dipole moment, which means to the left. Okay. Here also it will be to the left. So on the axial line, field is in the opposite direction of the dipole moment, and the magnitude value is also important, kp by r cube. Okay. So in the axial, there is only an extra 2 in the numerator. In the equatorial, there is no 2 in the numerator, right? So that is the field due to dipole. Okay. That is the field due to dipole. Yes, it will be kp by r cube. Okay guys, so I guess we can end it here. Okay. The rest of the topics we can take it in the next lecture. Okay. So yeah, you guys, if you guys have any extra doubts, you can ask. Okay. Yes, yes. So you guys can ask the questions now. I am looking at the chat. It's been 2 hours and 50 minutes. Okay. Any more questions, guys? Any more questions? Any doubts from today's lecture or in general? Okay, if there is no doubt, we can end it. Okay. Electric dipole is placed at angle 30 degrees with electric field 2 into 10 power 5. Okay. So the dipole in an electric field, I guess they're asking the torque, right? Anil, the question is it about finding torque? Yes. So for torque, I'll mention the formula, Anil, but actually that was the next topic itself. But yeah, it's about time now. That's why. So the torque formula, it is P cross E. Okay, dipole moment cross the electric field, external electric field. So in the question that you're talking about, if you want the torque, it is the magnitude of cross product, which is PE sine theta. So you can find the magnitude of the dipole moment, okay, which is the formula we looked at, right? Q into 2A or Q into distance between the charges. So if the distance between the charges is D, then the dipole moment is QD. Okay. This way you can get the dipole moment. Electric field is given to you. This is the external electric field, and this angle theta is the angle between P and D. Okay. So if the dipole moment is in this direction and electric field is in this direction, I guess the angle is also given, right? 30 degree. So you can just substitute it in this. Yes, so I'm an okay, Anushka. So that so basically, if the question is to find the torque, you will have to use this relation. Okay, so we didn't have time to derive this, but I guess it is clear now, right? Okay, guys. So we will meet in the next lecture. Okay, so we can end the lecture here. Yeah, couple force also I'll explain in the next lecture. Okay, goodbye guys, take care. Okay. All right. End करना था.